So in the previous session we were talking the idea that you can that if your particle approaches sufficiently close, the so-called little beta impact parameter, if it's small enough, you can get only a spherical wave, S wave type scattering. So what we'll do now in this session is give a justification. We'll actually use some concrete numbers to show that assumption is a good one, and it implies that the little l, the angular momentum quantum number, little l, in our formula that we've been doing the last few sessions, is 0. And that simplifies the math, the formulas. We can plug in L0 into the formulas, and that will help us find a simpler, easier formula for the deltas, the phase shifts. Alright, so let's take the case of so-called thermal neutrons. What are they? What's thermal about them? Well, effectively they're just slow neutrons. They're not super fast. Sort of moving around at the speeds that, say, atoms in a gas, just ordinary air, let's say, would be moving around. So in other words, slow, effectively. They're not relativistic. And so their momentum is low, and therefore their de Broglie wavelength is high. Okay, so let's plug in some numbers and justify why, for that case, the angular momentum quantum number, little l, is 0. All right. So for the case of thermal neutrons, so here's the mass of the neutron, which is almost the same as the mass of the proton. They're in many ways almost an identical particle, which is an idea that gets used a lot in particle physics, but that's another topic. Right? So the mass of the neutron is this 1.67 times 10 to the minus 27 kilograms. Let's say the energy is of this order, 6 by 10 to the minus 21 joules. Right? And if you know the E, you know what little k is. You do the math and you get 4.25 more or less 10 to the power 10 per meter. And let's say the interaction range, that's the distance over which the force acts, let's say, is of the order of about 2 femtometers, 10 to the minus 15 of a meter. One of my research interests, one of my obsessions, I've mentioned it before, but I'm looking into the possibility of a femtometer technology. So in other words, using phenomena that occur at those tiny scales, nuclear scales, a nucleon, quarks, gluons, that kind of stuff, to create a technology from it. Now, I've already, in principle, figured out a way how to compute, because your background is more computer science. Before I retired, I was a full professor in computer science rather than math physics. So, the femtoscale interests me. So the incoming particle feels a force so long as it's little b, which is the impact parameter, is less than 2 femtometers. If it's greater than that, it hardly feels anything, right? So so that means that k little r, if this is your little r here, and you've got your k, which is this much, you multiply that by 2 in effect, so you get 8.5 by 10 to the minus 5, right? Now that's your, and then you multiply, what's missing? So kr naught, h bar, oh I see, right. So if you multiply h bar k, that's the momentum of your particle, and this r0, the distance, so a momentum by a distance, that's an angular momentum, and so that will be equal. Now these are the allowed values of an angular momentum of a particle from the quantum mechanics of angular momentum, so it's h bar square root of L into L plus 1, and so that has to be less than this. Now you plug in the actual numbers, you can get rid of the h bars. We know kr0 is this value, and that's pretty small, right? 10 to the minus 5. And so the only way that this can be less than... Does that make sense? Well, is L a 0? Hold on. Oh yeah, of course. Yeah, L is 0. So if L is 0, this is 0. Okay, and this is very small. It's just 10 to the minus 4 more or less. Okay. The only way, this has to be very small. In other words, 0. So L is 0. Okay, and if L is 0, we're talking about, well, when we come to solve the Schrödinger equation for the hydrogen atom, in detail, then if little l, the angular momentum quantum number, is 0, then we're talking about an S wave, S for spherical wave. Talking about this a bit previous session. So if L is 0, we have an S wave, a spherically, it's an inner. An S wave is closer to the nucleus than the other kinds. P, there's S waves and there's P waves and so on. P, I think it stands for polar, meaning sort of angular, like wings or lobes that are dependent on the polar angle. Oh, that's probably where it comes from. Yeah, polar angles theta and phi. Okay, so in other words, for the other values of L, for L's not equal to 0, then these there's no scattering. Okay. So these delta L's for L non-zero is approximately 0. Right? So that means we can simplify things a bit. Now from an earlier, was it the previous session? I think we had a formula. I mean, you can't see it, but I'm looking at other parts of the board. Remember, this board here is nearly 3 square meters. It's a big board now. So I can see previous, what I wrote on the board for previous sessions, but you can't. So I'm just checking. So we had this formula, a little sigma, which is the total cross-section, is that right? Yeah, total cross-section. So the previous session we had a formula, we had a formula of this form. So it was 4 pi over k and times the imaginary part of f of naught, the scattering amplitude f of naught, where the actual angle is, scattering angle is 0, and the formula was, well, yeah, it was in the previous session, and it had some, in the formula there were some little l's in it. Well, if we put those the little l 0, there's only one. We had, look, I'll read it out to you. So the imaginary part of f of naught is 1 over k, the sum over from L to naught to infinity of 2L plus 1 times sine squared delta. Well, for all cases of L not equal to naught, the